All right, looking at the calendar, again, our test is on Tuesday, so it comes up on us pretty quick. I guess the good news is we'll be through with all the new stuff by Friday. You'll have the weekend to hopefully catch up on all the homework. You'll have the review sheet by then, because I don't think it's in the packet, but you'll have it by Friday, and then Monday we can talk about the review sheet, and Tuesday we'll be ready for the test. So a little bit of a quick turnaround. Hopefully you don't have any other tests early next week because we're out of the gate, but I guess we'll find out, or you'll find out. Unit 8, Day 2. This is about radians versus degrees.
Is that schedule, like, do we get our own copy, or is that going to be posted in Schoology?
This will be posted in Schoology, and I do intend to make copies for you, but I haven't done that yet. Well, it's not all about convert radians and degrees. So, Roman numeral 1, convert radians back and forth with degrees. 3 Roman numerals today, but they get shorter as we go. You've seen this before because we had to be in the right mode yesterday, radians versus degrees. And most students don't ever really understand what the difference is. They just make sure they're in the right mode in the calculator and go with that and don't worry about understanding it. Hopefully, we can fix that today and you'll understand why there's 2 things in the calculator, what the difference is, and how to go back and forth between them. Let's first think about a full circle, or a full spin around a circle. If you go all the way around, I swear if there's any skaters, if anybody was a skater in middle school, it's kind of a past thing now. Nobody's skateboarding. But what is it called if you go one time all the way around? How many degrees is that? 360. 360 degrees. Do you know how far it is all the way around in radians? Well, you may not. That's okay. How about the circumference of a circle? Do you know what the circumference of a circle is? That's area. Pi r squared is area. So what's the other one? 2 pi r is the circumference. Because the 2 pi part is the measure of the degree in radians, or measure of the angle in radians. So 360 degrees is the same thing as 2 pi radians. Degrees and radians are both ways of measuring angles. Measures of angles. Like yesterday, we had a problem that we had to know that 1 mile was 5,280 feet. You know that 3 feet is the same as 1 yard, and 12 inches is the same as 1 foot. This is the same thing. Now, 360 degrees is the same thing as 2 pi radians. So it's just a different way of measuring how wide an angle is. Some people remember this one, 360 equals 2 pi, because it's kind of easy to everybody knows that 1 time around the circle is 360. Most people can remember 2 pi r, and so you kind of take those 2 things together, set them equal to each other, and you've got your conversion. Another way to remember it is to just divide both sides by 2 and say that 180 degrees is pi radians. That's the same thing, right? That's like saying 12 inches is a foot, but 24 inches is 2 feet. Like, well, yeah, but it's the same thing. Same thing here. 360 is 2 pi, or 180 is the same as pi. Remembering either one is fine, but the 180 equals pi is probably going to be the one we want to use when we're doing conversions. So let's start by going from degrees to radians. How many of you have already had chemistry or in chemistry now? Show of hands. Most of you. Good. This seems to be a less popular topic in chemistry, but one of my favorite topics in chemistry was the train track thing. You remember that? Like taking care of units, like 22.4 liters per mole and moles per atoms and all the conversion stuff. Yes, no?
I do remember that.
You kind of remember that. You didn't like it, but...
I remember the packet for that.
I remember how we spent like a solid week or two making sure we knew how to convert correctly.
I liked it because you could get the right answer. This is a math person talking. You could kind of get the right answer without understanding what was going on. As long as the units marked out, you did it right. Like, who cares if you understood it? Not really, but you could get the right answer without understanding things. And that's a lot of physics and chemistry. I mean, that's not what we want you to do in physics and chemistry, but if you can make the units work, you can get the answer right. That's kind of the same thing here. So if I want to convert 60 degrees into radians, well, I want the degrees to go away, so I need the degree in the bottom. So 180 degrees is the same thing as pi radians. And again, I put it that way because I wanted the degrees. It's kind of weird to cancel out the little symbol, but it means degrees. Cancel the degrees, and I'm left with radians. So 60 over 180 times pi radians. That would reduce. That's an easy reduce. So pi over 3 radians. So we're always going to use the pi in 180. It's just a matter of who goes in the top, who goes in the bottom. But you don't memorize it. You just figure out how to make the units work. Let's do another one. Negative 140 degrees. See if you can convert that into radians. The degrees cancel. You're left with radians. 114 over 18, zeros will cancel, would be negative 7 over 9, because they'll both divide by 2. Pi's still there. We're in radians. Don't forget the negative sign. That's a common mistake on these, just because you get so involved in how do I convert it, how do I reduce it, make the units work, and then you forgot the negative. So be careful on those. All right, let's switch and go the other way. Let's go radians to degrees. So let's say we're starting with 5 pi over 8 radians. Okay, rather than putting the whole 5 pi over 8 in the top when we do the train track thing, the 5 pi is in the top, the 8's in the bottom, so just continue that train track thing like that. That'll make handling the fractions a little bit easier. Okay, radians is in the top now, so I want radians in the bottom to cancel it. So pi radians is 180 degrees. So it's a little bit backwards. But again, I don't memorize which one is which. I just figure out where it needs to go, where the units need to go to make them cancel out.
Wait, why'd you put that 8?
Why did I put the 8 in the bottom? The 8 was already in the bottom. Right? It started like that. I just sort of extended the fraction bar so that it would stay in the bottom. You don't have to do that, but it makes reducing a little bit weird if you do it. That wouldn't be wrong. It's just a little bit hard to figure out who's in the top and who's the bottom. So it's not wrong, it just makes things hard. Instead, extend the fraction bar that's already there and do your conversion off of that. All right, the radians cancel, so we know we'll be in degrees. The pi's cancel. And now I've got 5 times 180 over 8. Well, you've got a calculator, so you don't have to worry about messing this up. And we like our answers as fractions for these. So yes, it's 112.5, but let's do the math frac thing. Actually, for degrees, we do like decimals, so let's just leave it as 112.5 degrees. It's the ones with pi's in them that we prefer to leave it as fractions. All right, you try this one. Negative pi over 10 radians. Convert that to degrees. Again, extend the fraction bar is probably the best way to go. I want the radians to go away. They're in the top, so I want to put them in the bottom so that they'll cancel. But pi radians is 180 degrees. And then we just watch for things to cancel. The radians cancel. We force that to happen. That's what we wanted to happen so that we're left with degrees. The pi's will cancel. And then I've just got 180 over 10. That's 18. So 18 degrees. Why is that not right? The negative. Again, it's a minor mistake, but it could cost you 1 or 2 points if you're just not paying attention and remembering to keep that negative through the problem. Let's do one more, because occasionally I give you something that looks a little bit weird. Let's convert 5 radians to degrees. So same process. Want the radians to go away, so radians in the bottom to cancel. Pi radians is 180 degrees. The radians cancel. This time there's no pi to cancel. Okay, no big deal. I go to the calculator. 5 times 180 is 900. 900 over pi. That's okay as an answer, but since we're in degrees, like we usually only want pi if we're in radians. Like pi as part of the answer is okay if we're in radians. If we're in degrees, may as well divide it out and figure out what it is. Especially since most of you, all of you, think in degrees more than you think in radians. At least for now. By the end of the semester, that will change. But for now, everyone has a much better idea of what degrees looks like than radians, right? If I ask you to draw a 90-degree angle, all of you would do it without a protractor super accurately. If I ask you to draw a pi over 3 angle, most of you would be like, I don't know what that is. What do you want me to do? That's going to change as we go. But for now, we're more familiar with degrees, and that's okay, but this is sort of the process of getting us a little bit more familiar with radians. All right, questions on converting? It's just pi over 180 or 180 over pi. And again, I don't memorize who goes where. I just figure it out based on who I want to cancel. Yes, sir.
When do we change the mode on the calculator?
Okay, that's a great question. The mode on the calculator doesn't affect any of the stuff that we just did. Because the mode on the calculator only matters if you're going to hit one of those 3 sine, cosine, tangent buttons. Okay? So you want to be in the right mode, but it doesn't matter unless you're going to be using sine, cosine, or tangent. Right? Because the calculator doesn't know that we were in radians or degrees when we were converting these. So when you're doing conversions, it doesn't matter because you're just doing the math. It only matters for sine, cosine, and tangent. So that's a really good question. Roman numeral 2. Arc length and sector area. Sounds fancy. Arc length, sector area. First, arc length. Well, let's first explain what we're talking about when we talk about an arc length. We have a circle with a central angle central angle just means an angle whose vertex is at the center. So it can't just be like any random angle inside a circle. It's got to be a central angle. Then this piece of the circumference, that piece of the circumference is called an arc. So if theta was 360, you'd have the full circle. But we're not always going to have a full circle. We're going to have a half a circle or a fourth of a circle or some part of a circle that's traced out by 110 degrees or something. So we've got a central angle that creates an arc length. Let's start with the one we know. You said this one already. Ugh, if I can spell. Recall, the circumference is 2 pi r. Circumference is 2 pi r. Well, that's like a special case of an arc length. That's an arc length that's all the way around the circle. But that's a familiar one, so we've learned that one. But if we want just a different arc length, if we want to call this L, well, 2 pi was all the way around the circle. Is the angle measurement all the way around the circle? So that arc length is however far we go around the circle times r. So the arc length is theta times r. Again, the kind of unique thing is you've used this a million times before, but every time you've used it before, 2 pi was the central angle because you wanted the whole circle. But now we're going to look at pieces of the circle. The big catch here is that theta must be in radians. And I think that makes sense. If theta was in degrees, then the circumference formula would be 360r. But that's not the circumference formula. You don't multiply the radius 360 times to get the circumference. That doesn't make sense. Because theta has to be in radians. So as long as you're in radians, it's a real easy formula to use. We'll do an example combined with sector area in a minute, because they're pretty similar. Sector area. Let's draw a circle again. And let's even do the same picture. It has a central angle theta, has a radius r. That shaded area is called a sector. So you've done these before, but every time you did this before, it was the full circle. So like the sector was the full circle. But now we're going to get to half circles and third circles and whatever angle that is, circles. To me, the easiest way to remember the formula is to start with the area formula. So what's the area of an entire circle? Pi r squared. All right, well, we're not done with this formula because that would be the whole circle. So we want to adjust that based on how much of the circle we have. Well, how much of the circle we have is theta over 2 pi. All right, because if theta gets to 2 pi, then 2 pi over 2 pi cancels out and we're back to a full circle. If we're halfway around, like pi way around, then we'd be multiplying by a half. So it's sort of this adjustment factor to the area. This one you can get by with doing it in degrees. If theta is in degrees, what would this fraction over here be? 360. So on the sector area, you can kind of get by with doing it in degrees as long as you're careful. So I don't know if you want to memorize one formula and say it always has to be in radians, or just know both of them and be okay with theta in radians versus theta in degrees. So it doesn't matter. Start with the full circle and then adjust based on how much of the circle you have. So let's do an example that kind of has both. So let's find arc length and sector area for radius equals 4 inches and theta equals 110 degrees. Arc length and sector area. Radius is 4, theta is 110. I'm going to draw a picture. So 4 inches, 110 degrees. Okay, even if you're not great, at least it's in degrees. So if you're not great at angles, 110. What's a standard angle that's close to 110 that you know what it looks like? 90. So 110 is bigger than 90. Not a whole lot bigger than 90. So I don't know. My picture doesn't have to be perfect. I'd like it to be reasonable though. So something like that. A little bit bigger than 90. I'm not getting the protractor out and measuring to make sure it's perfect. I just want it to be reasonable. Alright, so I want the sector length, or excuse me, the arc length. Arc length equals r times theta. Except that theta's got to be in radians. So I need to change 110 degrees into radians. We know how to do that. That's what we did in the first part of this lesson. So let's see. I want the degrees to go away, so I need degrees in the bottom and radians in top. And pi radians is 180 degrees. The zeros cancel, so 11 pi over 18 radians. I mean, I'm not done, but that's my angle in radians now. So my arc length is 4 inches times 11 pi over 18 radians. So I could leave that as 44 pi over 18 and reduce it, but like I want to know how long the piece is. So I want to just go to the calculator and get a decimal for that, because 44 pi over 18, that doesn't tell me a whole lot. I mean, it's a precise answer, but it's unhelpful. 44 pi over 18, 7.68. And then the units are kind of goofy with radians, because when you need them to be there, they're there as radians. When you don't need them to be there, they can kind of go away. So if we're measuring arc length, that should be in inches. So 7.68 inches. And that's kind of weird. The radians are, sometimes they're a unit, sometimes they're not. And then sector area, pi r squared times, I'm just going to leave it as 110. 110 over 360, because that's the portion of the circle that I'm looking at. So the green sector area, that weird looking pie piece, I guess. That's a large piece of pie though. So pi times 4 inches squared times 110 over 360. Again, that's a answer that's correct, but not real helpful, so I want to put it in the calculator. 16 pi times 110 divided by 360. 15.36. What are the units of that? Inches squared. For one of two reasons. One is, well, I squared inches, so I've got inches squared. A different reason would be I'm doing area, so I know what area units are. That's inches squared. You can go to 2 unless it says otherwise. That's exactly what I was just looking at on the worksheet to see if it specifies, and it doesn't. So 2 decimal points can be fine unless otherwise stated. So be careful. All right, I'm seeing if we can get to what I want to get to today or not. And I don't think we can, which is unfortunate, but I think tomorrow is short enough that we'll make it work tomorrow. Bah. Tell you what, we'll start it. I'll make tomorrow a little bit easier. So the homework today is worksheet 2, but we're not going to be able to get through all of it. I think you can do 1 through 20. Eventually we'll get to all of it. We'll start with 1 through 20. Let's talk briefly about velocity. And maybe this will be where we end it. Give you something to think about and ponder the wheel here. So if I give this wheel a spin, I got to do this on camera. There's a yellow post-it note, a pink post-it note. My question for you is, which post-it note is going faster? The yellow or the pink? Why do you say yellow? Okay, so someone says yellow because it's going in a bigger circle. Okay, that sounds reasonable. The yellow is like tracing out more. I buy that. Adam, what are you saying?
I mean, I think it's the same, but I don't know.
And one person says they're the same because they're like on the same wheel, attached to the same spoke even. So, like, the spoke's not moving. Like, so if they're attached, shouldn't they be going the same velocity?
Well, they're probably traveling the same speed, but velocity-wise, since the yellow's covering the distance, they're not more.
Okay,
But
so
they're doing the same number of rotations at the same time.
ooh, that's a really good observation. They are doing the same number of rotations. They're definitely doing the same number of rotations.
So that means that the yellow one's going faster.
But Andrew is still claiming that the yellow one's going faster.
Yeah, 'cause it's got a
But
bigger
it's
area.
covering area.
It may not
Because it's
be-
covering more ground. I don't know if you wanted to use the word area, but it's covering more distance
Yeah.
because it's a bigger circumference. And it turns out you're both right. Like, in some ways, in one way, they are going the same speed, right? Because they're attached.
But speed and velocity are different. They're going the same speed, but because the yellow is covering the distance, it changes the velocity.
Okay, you're on the right track. It's not speed versus velocity. It's angular speed versus linear speed, or angular velocity versus linear velocity.
Vaguely know what that is.
What is that?
Stop here in just a minute. Angular velocity is omega. That's a Greek letter. It's measured in radians per second, sometimes revolutions per second, or revolutions per minute. RPM, you've heard that probably with cars maybe. RPM is revolutions per minute. That's an angular velocity, how fast something is spinning. Velocity you're more familiar with. That's, feet per second or miles per hour. That's a distance thing. How much distance is covered? So with the bike wheel, you were both right. The yellow one was going farther in the same amount of time, so it had a higher linear velocity. But they were spinning at the same rate, so they had the same angular velocity. And on tomorrow, we'll look a little bit more at how they are related to each other. So there's the preview for tomorrow. If you know how fast it's spinning, you multiply by the radius, and you get how fast it's going. I think that makes sense, because the bigger the radius, the faster it goes, right? If I slid my little yellow one down to here, well, it still has the same angular speed, but now it's not going quite as fast as it was when the radius was all the way out here, because now it's got a bigger radius. It's got to travel more. It's got a bigger velocity because its radius is bigger. So, kind of a weird deal that yes, they have the same speed, but no, they don't have the same speed. And the difference is angular velocity versus linear velocity. All right, that's what the rest of the worksheet's on, but we'll work some examples on that tomorrow. So your assignment today is 1 through 20, but we'll get to the rest of them tomorrow.